As I mentioned on the group chat, today is going to be today and tomorrow are going to be the last classes that we're going to have. So um today is supposed to be the last embedded systems class. I think what I'm going to do for today's class, because we've already covered most of everything. We've worked with the Arduino, we've worked with the ESP32, we have worked on different projects, um knowing how to work with different sensors and different components, so that as we do that, we can take different readings from the environment. And not just that, I think that we've also given different assignments on how you guys can combine them and integrate all of them together a to serve a collective purpose. And um in the last two classes that we have, Afolabi walked you guys through to how to function or how to think as an engineer. That it's not just about knowing how to write code and knowing how to program different sensors. By the end of the day, the thought process is what really makes an engineer an engineer. So I think we've done justice most of that. So for this last class, I think what we'll just be doing is just covering power management, and um, also understanding how, like, I know that the introduction to electronics class, we covered a whole lot. We spoke about um, resistance, current, voltage, power, and so many other things. Sorry if my voice is so, like, I don't want to call it sore throats, but like I actually don't know what is wrong with my throat, but something is sure wrong with my throat. Anyway, we covered quite a number in the past. How many weeks? I think this is 8 weeks. So today, since we've already done like combination of different components, and knowing how to program all of them so they all perform their different tasks to a common goal, I think what we're just going to do today is just to cover the last parts of electronics that are still not really talked about, but they are still very important because they determine how well a what is the word I'm looking for? They determine how well the project is still going to perform, because whether we want to accept it or whether we realize it or not, power management is still something that is very important. So let me see if I can get my whiteboard so that I can't tell you last time. Oh, it's not this one. Sorry, please hold on. Not so long. Okay, found it. Mm. Okay, so let me share my screen. Mm. You guys can see the screen, right? You just confirm. Nobody is saying anything. Can you see my screen? Mm. Okay. Mm. The screen set also share. Okay. So for this last class, I'm going to walk us through um oh, wrong side. Going to walk us through. Okay, good. We have inductance. If only I had a pen for this thing. Inductance, capacitance, um, capacitance. We have impedance, and last thing is basically power management and battery life. Hmm. Hmm. So all these four here. Okay. So these four things are what we'll be covering in this last class. Why? Because you are going to work with whenever you're building circuits, even in the PCB designs that you're going to be doing, you are going to need to take into consideration not just the active electrical components, but also the passive ones, because the passive ones are going to help in like filtering how the electricity passes through the circuits. They are going to um they are going to help to reduce instances of short circuiting, and they are also going to basically increase the efficiency of whatever circuit it is that you are building or that you are working with. And a lot of times, you'd even see that on the microprocessors that you or the microcontrollers, sorry, that you are using, these different microcontrollers that are using these different passive components. You would see them a lot. Maybe they are diodes, maybe they are LEDs, maybe they are capacitors, but you may not know that is how they look. Maybe they are inductors also, but you may not know that, may not exactly know how they look or what their importance is. So what I'm supposed to do is just help you to understand that, oh, as much as these things may seem like, I don't want to say insignificant, but as much as they seem like very small, they have very small significance. They still play a very big part in the. They still play a very big part in the building or construction of a circuit, essentially. So first thing is inductance. So what is an inductor? An inductor is basically how, like the way we have resistors, and resistors are electrical components that slow down or resist the flow of electricity. The reason why they are so important is because a lot of times, like if electricity should run in a circuit, let's assume from the power source now, let's say this is a battery, to the ground, to the load. Let's use this LED now, for example. This LED will be our load, and then we have our ground. In cases like this, sometimes, like when electricity just runs without any resistance or without anything slowing it down, there are going to be instances of short circuits, because in this case the current or the electricity is running through the circuit so fast that if care is not taken, this LED may actually burn, and that would be a waste of money, even though LEDs are like 20 naira. But a imagine that you have probably another component that is, let's say, 10 times as expensive, or 10 times as expensive, like, or 1,000 times as expensive. It's going to be a very costly thing. And at the end of the day, something that is very even if hardware, as a lot of us know, is going to cost you money, you want to reduce the wastage of money as much as possible. And that is where some things like resistors, capacitors, inductors come in, so that cases of, something burns or your circuits blew up, cases like that won't be as frequent. Yeah, cases like that won't be as frequent. So you have your resistor acting as the load in that circuit, so that that LED is not going to burn, or there's not going to be a case of, money has now gone down the drain. So what does an inductor do, or how does it work? Hmm. Why can't I find my pen now? Hmm. Okay. So let's imagine that you have, let's say, a tap here. I don't know. I like to use taps as example these days because they are the easiest to follow and to understand. Let's assume that you have a tap here, and then there's now a pipe that's flowing here. And this pipe is flowing in a loop. And as this flowing in a loop, there are actually two parts in that loop. And let's assume that in this second, in this second, let's say, pathway, yeah, in this second pathway, there is actually a water wheel inside of it. And this water wheel, based on how much the water the water has force that pushes through the water has force that pushes through the pipe. Based on how strong that pressure is, or that force is, it will keep flowing, or it will remain stationary. And then when the pressure is now much, it now keep flowing. It's now keep it's, it's very efficient. Mhm. Okay. Mm, this is how it will work. There are two pathways. Mm, okay, there are two pathways. Sorry. There are two pathways, and this pathway leaks out to somewhere else. Let's say this is to a tank somewhere. So the water is going to flow through a tank. So as this water flows through this tap, as you turn on the tap, water flows this way, the path with little to no resistance. The water will flow through this because there's no resistance through that path, and the water is always going to choose the path that has little to no resistance. So since this water wheel now is there, there's going to be a form of resistance in this whole like circuit. There's going to be a form of resistance, and um the water will keep flowing and keep flowing and keep flowing. But then let's assume that at some point you would there was now like a blockage in this place, meaning that, oh, the tank is full and then we don't want any water to keep flowing through, to keep flowing out of this whole pipe system. So as it keeps flowing, it keeps flowing, it keeps flowing. Because this part is now blocked, the water, and then this part is now full. The water would now decide that, okay, since this part with little to no resistance is already full, let's now pass through this side. And then it was passing here, there was no resistance here. It kept flowing with ease. A little bit of water will still pass here, but then the pressure and the force that it is going to use to pass this side that has the water wheel is not so much. And as a result, water will still build up here, but then little pressure will keep being applied to this water wheel, and the water will be moving gradually, 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 till it now gains momentum. And then as it gains momentum, and then it keeps turning, and then it starts to turn little by little, little by little, till the force and pressure that is applied to this water will now increases. So um, as it now increases, the water will keep flowing, and then this you'll now notice that there is now little to no resistance in this whole water wheel part, because enough pressure has been built up. Enough pressure has been built up on this part that has the water wheel. So the water wheel is now acting the part of the water wheel is not acting like there is no water wheel there at all. There's no load, there's no resistance, there's nothing like that. And so the way it would have normally moved in this first part here is the same way it would now move here, because the pressure that has been applied to it has now made the rate of flow in this water wheel part and in this part that has little resistance to be the same, meaning that there's no resistance. So as that continues, let's assume you now turn off this tap. As you now turn off this tap, obviously, like, water is going to stop flowing here. And then at some point, when, because there is no more pressure being applied to this part also, you'll now notice that this part will stop also, and then this part will stop also. That is what happens in an inductor. Yeah, that's what happens in an inductor. Basically, an inductor is an electrical component that builds up um it's an electrical component that builds up momentum, that stores up electrical energy, and then as it stores it up, when the pressure that is being applied, or in this case, let's say the electricity that is being applied to that inductor it has reached a certain level, it will now act in such a way that there is no resistance flowing through it. So when the pressure that is being applied to it is not enough, it will keep acting like a resistor. Oh, you keep pushing it, you keep pushing current through it, you keep pushing current through it, keep pushing. Let me even draw like a stick body now. Like, you keep um pushing the door, trying to push the door open, trying to force electricity is trying to force its way in. Then, Dominion, you have a question.
Ok- I'm trying to understand something.
Mm-hmm.
So is inductor, is it like it's doesn't allow the flow of electricity until it reaches a certain level or
Yes, exactly.
a certain limit? Okay, that's just what it does.
Yes, that's exactly what
Oh,
I'm saying. So it's like, you know how semiconductors work, where um if they are if there is no heat applied to it, it is going to act as an insulator, right? Right. You know how conductors work and how insulators work. Like, conductors are um materials that allow electricity to pass through them. Insulators are the opposites. And we know that semiconductors, how they act is that at a certain temperature, when there is no heat applied to them, they act as insulators. But then when let's say heat is now applied to it at a particular temperature, and now they now start acting like conductors, right? So that's the same thing that's happening in this case. But in this case, instead of heat, it is now electricity. So at a certain point, when there is no um when voltage is being applied until it reaches like a particular threshold, it's going to keep acting as a resistor. But then once it now hits that threshold and it passes it, it now acts like a normal electrical component that allows electricity to flow through it. So the more you push and the more pressure you apply, or in this case, the more voltage or electricity you apply to the inductor, it now builds it up. And then because of the resistance that was applied to it, it is going to create something that we know as a result, it's going to create something called a magnetic field as a result of the pressure and the resistance that kept being applied the back and forth and back and forth. So in the last PCB design class, Ebuka showed, oh sorry, on the group chat rather, Ebuka showed there was an image that looked like this. That, oh, this is basically an electrical field and how the electricity keeps passing through from one point to the other. But then when you now have a build-up of this electrical field and then there's now some sort of resistance, you will now see that it's still like this, that the electrical field is still there, the electric field is still there, but then because of the build up and the resistance, there is now like a magnetic field that is being formed as a result. This magnetic field is now what will now like keep allowing this electricity, even when the flow from the source, in this case the tap, has stopped, the thing that will still keep making this water wheel and keep pushing it and pushing it so that it will keep turning, that is the magnetic field at work. So it will keep pushing it and pushing the electricity and pushing the electricity through the circuit till it now like runs out of, let's say, like the intensity or till the influence of the magnetic field now reduces and then it just dissipates. Do you understand? So basically, that is how inductors work. And inductance, based on person that made it, inductance is measured in Henry's. So the measure at which this happens is now measured in Henry's, and you write it as H. Please do not mind my horrible handwriting. Oh yeah, that's how it's going to be. So the next thing now, I think I can wipe this part. I'm trying to find my eraser. I can't find this eraser now. Mhm. Okay, so that is it for. So any other questions before I move on to capacitance? Okay, I'll take it. I explained it very well. Then capacitance now. Capacitance. Okay. Then capacitance now. Capacitance has to. Let me look for an analogy to use that will actually help to do this thing. Okay. So a capacitance now is capacitance is okay. So what is a capacitor? This is actually not the symbol for capacitors. But let me just use it because I think this will be the easiest way for me to explain how they work. So this is the negative part and this is the positive part. Capacitors are electrical components that store up energy or that store up electricity, and they store it up in such a way that even when I think now um I'm really going into electrical or electronic components that store up electricity and also allow for like the smooth passage of electricity after a threshold has been reached. So capacitors are electrical or electronic components that basically store up electricity, and as a result they help to smoothen out how this electricity is going to flow, how this electricity is going to flow in that circuit, even in the case of, oh, there is no more um even in the case of, let's say the power source has been cut off or there is no more flow of electricity. So let's use for instance now that we have a light bulb. Mm, yeah, let's say we have a light bulb here, and oh, sorry, getting distracted again. Let's say we have a light bulb now, and then this light bulb has positive end and the negative end. And then as this electricity flows, there will be ground, of course. There will be ground. Move it up a bit. And then in between, there is now a capacitor. Symbol for capacitance, oh sorry, symbol for capacitor is like this. This shall the symbol for capacitor, so please don't mind if it looks very strange. That shall the symbol for capacitor. Mm, where's my okay? So this is shall the symbol for the capacitor. So think of it like this. So where's the power source? Think of it like this. This is where the power source will be, even though this is kind of unrealistic because of course it's not going to be here. I need to take this thing a bit slower. So let's say the power source is now here, and let's move up. Mm, Okay, so this is ground. Yeah, so think of it like this. This power source is connected to this whole thing. And as I said, the same way this tap will work, the electricity or the tap that I drew earlier, the electricity is always going to select the parts with little to no resistance. And how this capacitor works is that as as electricity keeps flowing through it, at some point it will move. Okay, this is the capacitor. And as electricity keeps flowing through it, it has a positive side and it has a negative side. What actually allows this electricity to move is a the movement of, we all know protons, neutrons, electrons, movement of electrons from a positively charged part, from the negatively charged part rather to a positively charged part. So how this happens is, as it keeps going, as the electricity keeps passing through this capacitor, there is a buildup of electrons here. These electrons are negatively charged, and that is what makes this part of the capacitor to be negative. So there are electrons, 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 electrons here. Then there is like a junction here that divides the positively charged parts and the negatively charged parts. So as electricity keeps moving or passing through this capacitor, these electrons will now be pushed from the part that has from negatively charged part, because positive attracts positive, negative, negative attracts positive. So it is going to migrate from this negatively charged part and then come to this positively charged parts, and the electrons will start to move one by one, 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 till let's say this electricity now stops, like the electrons or this part of the capacitor is full of electrons and it cannot accept any more electricity. Do you understand? So like the as electricity keeps passing through this capacitor, it keeps migrating as it has been stored up on the negative part, and then there is now a flow. It keeps moving to this positively charged part, keeps moving, keeps moving, keeps moving until the positively charged part is now full and there can be no more allowance of electricity flowing through it. So when that happens, in the case of this light bulb now, this electricity is going to keep passing. But then, as I said, the same way I explained it when I was explaining the tap and the water wheel, just because there is much resistance on the part that has the water wheel does not mean that water is not still going to keep passing through that water wheel path. Just that the pressure that is being applied is going to be little. But there is still tiny water that is going to flow from there's still tiny water that is still going to flow from this tap, hit the water wheel, till eventually the pressure that is now being applied reaches a certain point, and then this water wheel will now move, and then water will now start flowing through that part. Do you understand? So just because this load is here, in this case the water wheel, or in this case of the light bulb, the capacitor, just because there is a load here does not mean that at some point water is not going to keep entering, or electrons are not going to keep passing through or entering the capacitor. Do you get? So as this happens, small stocks of these electrons are building up on the positive part of the electrons. And then when it is now eventually full, as electricity keeps flowing, and then this light bulb now comes on, and then this light bulb now comes on, the electricity will keep going and keep going and keep going till at some point this capacitor is now full of electrons and there can be no more flow of electricity through it. What will now happen when at some point you now turn off the power source, or you remove this power source altogether? You remove this power source and then now there's no more flow of electricity. This light bulb is going to remain on. The current or the electricity kept passing, pass through, kept passing through, kept passing through, kept passing through, kept passing through, going in a full cycle till the source is now turned off and there is no more electricity that is flowing from the source. But there are still electrons, or there's still a little bit of electricity that is inside this capacitor. So as a result, this light bulb is not going to, because the light bulb is connected in parallel to this capacitor, this light bulb is not going to go off immediately because there is still stored up electricity inside of the capacitor. So this capacitor is going to need an outlet to discharge and to let go of all the electrons that are stored up or built up before. So as it keeps discharging it, this light bulb will continue to be on till it has now released all the electrons that are inside of it. And then as a result, the light bulb will now turn off. And then there is no more electricity flowing through it whatsoever. And you'll notice that this is the reason why a lot of circuits that have capacitors, when there is no power source that is being connected to it, that is just purely made of capacitors, the whether it's an LED, whether it is a light bulb, is not going to go off immediately, because at the point that the components were connected to the source, it was not there was a build up, or the capacitor was charging. And as it is charging, once there is no power source, once there is no like power supply again, it is going to need an outlet to discharge. And in this case, the LED is what is going to keep receiving that those electrons that are being discharged from the capacitor. So it helps like filter out this thing. So even if there wants to be, like, let's say, electricity supply, like now a lot of times, like, let's say in the country that we live in now, there are a lot of times where the NEPA can be silly, and then we have a lot of our appliances connected to, let's say, the sockets, and not all of them have like this power regulatory fuses. Or let me even see if I can even find it, like these fuses that they usually attach to our refrigerator connector, something. Mm, charge protector. Let me try to find a picture so that it can better illustrate what I'm trying to say. Yeah, so things like this. Now, you see that, if, yeah, thank you very much. So if at any point, let's say NEPA decides to be funny, or AEDC decides to be funny, and then AEDC decides to be funny, and then at different points in time, the power keeps going on and off and on and off and on and off. If there is any appliance that is connected to it, and then there is no um surge charge that is being connected to it, that thing is going to blow. But then, because this our refrigerator, whatever it is connected to this thing, has these things, it is going to take, let's say, like 10 seconds to 5 seconds before electricity will now be released to whatever it is connected to it. I don't know, I'll use fridge, because in my house it's mostly fridges that we use them for, or fridges that we connect them to, because we don't want them to blow. So things like this are kind of like what um are kind of like a somewhat good example, partial example of what capacitors do. That, until this thing reaches, let's say, a certain threshold, the electricity is not going to, that 5 seconds or that 10 seconds that it waits before it now releases electricity to whatever it is connected to it. That is now like what a capacitor does in this case. So it's going to wait until that threshold has been reached, until that what's the word I'm looking for? Until all the criteria has been met, essentially. So that is what a capacitor does. So it prevents like cases where, there's no filtering of the electricity that is passing through the light bulb. If now there is a sudden voltage spike, the diode will protect this light bulb from it, or whatever appliance is connected to it from it. Understood? Or any questions before I now move on to impedance? Okay, I take it I explained it well. The next thing is now impedance. Impedance is kind of kind of hard to explain, but take it that impedance is another form of resistance. But in this case, like a combination of resistance, inductance, capacitance. Oh, sorry, and also capacitance is measured in farads. Hey, sorry, I horrible handwriting. Capacitance is measured in farads and sometimes written as F. Yeah. So just take it that impedance is like a combination of all three: capacitance, inductance, resistance, and it's a different kind of it's a different kind of resistance that combines all of them. Like now, in cases where you have a circuit that has a conductor that has all three: a conductor, a resistor, a capacitance. Impedance is like the collective measure of resistance of all these three components in one. Yeah. So I don't think I'll go too deep into what impedance is about. So now let's talk about power management and battery life. Because when you are building a circuit, for you to find a battery that meets the criteria or that is sufficient enough for all of this, for you to find a battery that can carry all this load that you are using in a project using in a project or in building a circuit, you will need a battery that can withstand the load. You will need a battery that can withstand the load, like the total load, everything that the circuit is made up of, everything that the circuit is carrying. So just list, let's say, 5 components. Think of a project and then list like 5 components that are going to be used in that project. And then we'll now calculate the battery life, or the battery life in this sense is like you getting the power ratings, voltage rating, and current rating that this battery must have for this project to last a reasonable amount of time. And in this case, let's say a reasonable amount of time is like 30 minutes to 1 hour. Let's not go too far. So let's say 30 minutes to 1 hour. So think of like 5 different components that you want us to work with, and then we'll calculate the battery ratings that we are going to need to make this project run. So just list out like 5 random, including the microcontroller, 5 random this thing, or just mention 5 components, and then what microcontroller of choice you want to use. So let's do that, and then we'll calculate the battery life. This is the best way for me to explain what battery life and power management is about. So let's go. Just 5 random components. You can type it out, or you can mute your mic and I'll just write it. Anyone. Hey, Sean is saying Raspberry Pi. Raspberry Pi that I've not even gone into. Not passive components, not passive, active ones like temperature sensors, ultrasonic sensor, DC motor, things like that. Yeah, not the passive ones, the active ones. Up amp is still a passive, it's still passive somewhat. I've only seen one component that I want to use. And Sean, please choose a microcontroller that we have worked with in our classes. So either Arduino or ESP32. Is there S8? Is there actually S8? Mm-hmm. Mm-hmm. I think there actually S8. Not seen. Bum, 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 bum. Mhm. There's no ESP32 S8, sure. I think there's just S2 and S3. And then programs for sensor S8. Just sensor. Mm. Okay. Mm-hmm. So S3. Okay. Nothing is wrong with Arduino. Don't mind. You could have suggested Arduino, but it did not suggest. Camera module. Okay, no problem. Camera module. What else? No other sensors. Nobody is saying anything about sensors. I've only seen ESP32 now. Proximity sensor. What kind of proximity sensor? I'll take it that it's infrared proximity sensor that you're referring to. But then there's passive infrared sensor also. Sure, sure, sure. I think I will use infrared proximity sensor. Which other one? I need like okay, okay. So let me write it out. Let me write it out. Mhm. So we have the ESP32. We have where's my handwriting now suddenly becoming big? We have the ESP32. We have um proximity sensor. Let's say the sorry, IR proximity sensor. We have what else again? IR proximity sensor. We have what else? What else? What else? The motors. What kind of motors? Drone like motors. That's like the brushless DC motors that are okay. Brushless DC motors. What else did you mention? It's a camera module. You have to be specific, but we'll just browse through. Camera module. Mm-hmm. Camera module. Okay, so 4 brushless DC motors. Okay, so this is what we are going to do. This for this for. So what we need now is we need the maximum. Why is my handwriting just becoming more horrible? God. Anyway, what we need is the maximum input voltage. Maximum input voltage and maximum input current for these components. And then having these two, we know that power is a product of voltage and current. So from knowing these two, we'll now know the maximum power that these components require. So what I will now do is um I will now go to my best friend, which is Google, and I'll ask Google that, oh, what is ESP32. What is the maximum input voltage and current of an ESP32? And Google, as the wonderful entity that it is going to tell me that honestly, I think that the ESP32 can receive more than. You can typically supply 5 to 12 volts to prevent it from overheating. So let's say 6 volts, I guess. General purpose pins, blah blah blah. Or should we just look at the data sheets? Should we look at the data sheets? Okay. Let's just look at the data sheets. Okay. So this is going to take time. Looking at the data sheets, Bluetooth, CPU, memory, clock, timers, referrals, power management. This data sheet is so unnecessarily long. Anyway, watchdog timers, blah 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 blah. So it is going to tell me that dual core, blah blah blah. Okay. How will I know if this is input or output? I feel like this is output. Comparison package, blah blah blah. This cannot be it. Oh, wow, I was wrong. 3.6 volts. Power supply. I don't want to believe you. But data sheets don't lie. But I don't want to believe it. Because you can still send 5 volts to it. Anyway, this is why. The maximum voltage that can be applied to the pins are 15. But you can power it with 5 volts. What are these people saying? Anyway. Directly 3.6. So let's just say 3.6. Let's just say 3.6. Connecting it to a pin 5 volts can fry it. Maximum linear input is this. Via the VIN or 5 volts pins. Highly recommended to prevent overheating. But I can send 5 volts to this thing. I don't know what these people are saying. But no one. I will not argue with the data sheets and with AI. So let's come back here. So maximum for this is maximum for the ESP is maximum for the ESP is, should we go with 3.6? Let's say 3.6. 3.6 volts. And then let's ask for the current. Yeah. Current, deep sleep, active with this. Peaks up to 400 milliamp. Important notes: when selecting a power supply, you should always ensure that it can provide at least 500 milliamps to 1 amp to prevent it from browning out or freezing over. So do we say 500? Always ensure that it can provide, not that it needs. Let's say 500 milliamp. Be on the safe side so that we're not fry it. I'm always struggling to find this mirror up. Okay, so come back here. So in this case, 36, 3.6 to 500 milliamp. If only I had a pen. Now this handwriting will not be ugly. Sha, next thing is for the proximity sensor. Let's say infrared um proximity sensor, um input voltage. Yeah. Okay. So more standard IR proximity sensor. Let me show you how it looks. This is the one I'm referring to. This one that looks like flame sensor. I don't know why you people do not want to use flame sensor. Because maybe it's because I like playing with fire sometimes. But anyway, like this one that looks like flame sensor, this one that has transmitter and receiver. That has, yeah. So that's the one I'm referring to. Ah ha ha ha. So standard input voltage for this is 3.3 to 5 volts. So let's say 5 volts. Yeah. Let's say 5 because majority is saying 5. And so let's say 5. Which message am I receiving? Who is DMing me? Hi guys, I'm sorry I've not been active. I got sick. Anyway, sorry. Let me come back to mirror. Share this tab. For infrared proximity sensor, it is 5 volts maximum. Then come here. Let's look for current. Let's look for current. Maximum input current. An infrared sensor typically draws an input supply of 20 20 milliamps. 20 milliamps. Anything that objects to that. This one says 30. Well, I believe AI, even though sometimes it does not have sense. But let's say it's 20. Let's say it is 20. Should we check here? I feel like instructable to have something sensible to tell me. Mm, blah 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 troubleshoot blah. Hope you did not have anything to tell me. So let's go to 20 milliamps. Back to the drawing board. So this is 20 milliamps. I'm so sorry, this is so basic. Yeah, 5 volts, 20 milliamps. And next thing is brushless DC motor. So this is the brushless DC motor that I believe that you have in mind. Brushless DC motor. And then we need ESCs for this kind of DC motors. Oh God. Anyway. Brushless DC motor input voltage. The thing about this type of brushless DC motors is that it always need an ESC. ESCs are electronic speed controllers. So for the kind of DC motors that I'm imagining, what I'm thinking about. Let me even show you. For the kind of brushless DC motors I'm thinking about, these are the types that I'm thinking about. These ones, these orange ones here. Those are the types that I am thinking about because those are the ones that are commonly used in drones, the ones that I've worked with anyway. So these orange ones, and I would go to Hub 360's page to check for the power rating and operating voltage 7.4 to 11.1. What of current? What of current? What of current? So we have 11.1. Current rating typically 15 to 20 times 4. So for the brushless DC motor, voltage is 11.1 volts and current is 20 amps times 4 sha. So keep that in mind. And as I said, when you're working with this brushless DC motor, you're going to need ESCs, so electronic speed controllers. So there are different types actually. There are the ones that supply 20 amps, 30 amps, 40 amps. But I think in most cases, people would rather use the one that have, to be on the safe side, 30 amps. Sure. Mm, I would much rather check microscale for this thing. Okay. So microscale is another this thing that supplies. So shameless plug to them. And then also to YFE because we'll start supplying electronics soon. So 30 amps for this and 16.8 volts. 30 amps. Mm, should we say 40? No, let's use 30. 30 amps, 16.8 volts. 30 amps, 16.8 volts. Okay, so coming back to the drawing board, let's write it down. Since we're working with this type of brushless motors, we have to use ESCs. And these ESCs, 13 points. Is it 13 points? 16 points, sorry. 16.8 volts and 30 amps, basically. Then the camera times 4. Times 4. Then the camera module. I wonder which camera module Sean wants us to use. Camera module. Let's just assume. But then if we're using this ESP32, we can just use this S3 that has a camera built on it. It's not be bad though, it makes sense. Let me type it. ESP32 with inbuilt camera. Oh, I made a mistake. It's inbuilt camera. Yeah, the S3. Yeah, the S3. This is the one that Saka was using. I'll be used this week. So the S3 with camera board on it. So this will just save us stress. And let me try to find the ratings. There are no ratings. I have to look for, okay. Operating voltage 3.6. Current anywhere. Current anywhere. I guess I have to look for it by myself. We'll have to look for it by ourselves. So 3.6 sha for the this thing. 3.6. Mm, it's okay. So yes, with S3, S3, sorry, S3 with camera input. I feel like the input currents will be the same, sure. Yeah, okay. Sudden spikes. I don't want to take that into account. But sure, let's say 350 milliamps. 350 milliamps. And because of the sudden camera spikes, you can use a clean power supply capable of 2 amps. Are you are you anyway, 350 milliamps and 3.6 volts, I guess. Anyway, 3.6. 3.6. Back to mirror. The ESP32 in this case 3.6 and then 350 with the camera, the active camera 350. So what we're going to do is that we're going to add all the currents, add all the voltage, then multiply everything and then give us our power. Then after doing that, okay, let's just do it turn by turn. Where is my phone? Or can somebody just quickly calculate it? This is becoming tinier by the minute. So what are we calculating? 3.6 plus 5 volts plus 11.1 times 4, because we are working with 4 brushless motors, plus 16 times 8, 16.8 times 4, because we're also working with 4 ESCs, plus oh, I think that's all. I think that's all. So what is the answer? This will be our total voltage used or consumed. So what will be our answer? 6K. Why are we using 6? Sorry, I don't see the message on time. Why are we using 6? Um, why are we using 6 motors? Sean, please explain. And why are we using 6? Daniel, welcome. Our committee of professional latecomers. But no shade, but shade, but no shade. Anyway, before you came, we delved into capacitance and no particular reason. Please let's use 4 because 4 is standard. So let's just use 4 because any drone that you see today is mostly 4. It's mostly 4. Like there are few that have 6. I think I've seen some that have 6, but standard is usually 4. So let's just use 4. Before I was saying that before you came, we have spoken about we explained impedance, inductance, and capacitance. Now we're discussing battery life. Please, can somebody calculate everything for me so that we can move on? Or do I just get my calculator? My calculator that will not disappoint me. Calculator. So what are we calculating? 3.6 plus 5 plus 11.1 plus I don't know why nobody wants to help me to do this calculation, but no problem. 16.8 plus 16.8, 16.8 plus 16.8. So it's 120.2 is what I got. So this is the total. Um, where is it? Where is my mirror board? Yeah, 120.8. Sorry, point two. 120.2 volts is total voltage used. So now let's do the same for current. For current, we have what's oh my god. Okay. For current, we have 350 plus 350 plus 20 milliamps ish plus 20 milliamps plus 20 amps times 4 plus 30 amps times 4 equals what? My calculator. So 350 plus 20 milliamps. Oh, if we convert that to amps, okay. If we convert that to amps, that's 0.35 plus 0.02 plus 80 plus 120. And that would be 200. Hey, crazy. 200.37 amps in summary. Then I keep that one. Okay, so this is it. So now we have to calculate power. So power is formula for power is current times voltage. So that's what self 120.2 times 200.37. That's a lot, but sha sha sha. No, no, no. Where's my calculator? Ah, where did you run off to? 120.2 times 200.37. So let's say approximately 24 kilowatts. They gave me this 4,000. Why did I cancel it again? Princess Yusuf. 200 plus 0.37 times 120.2. Shift this here. Minimize it. Shift it here. Please do not stress me out. 128 4 474. 474. So approximately that is 24 kilowatts. So now what we're going to do is to find a battery rate. Something is off. Something is off. If the current that is being supplied to all these things and require each of them has current draw. Each of them has current draw, and each of these ESCs, and each of these ESCs is demanding that it supplies 20 amps. But then they're all connected in series. Current in series, it's not the same thing. Is it in series or in parallel? If it's supplying from if the ES is what is supplying the power from the battery source to the brushless motors, does that mean that it is not negligible? I think so. I don't think the power being supplied to the ESCs, because if the ESCs have enough power being supplied to them, and they are the ones that are controlling the power being supplied to the brushless motors, I don't think the power being supplied to the brushless motors applies here. So, hmm. And I think they're all in parallel at the end of the parallel, the right word to use. Yes, I think so. I think so. Hmm. I don't think it's right for me to multiply them by 4. Because realistically speaking, there is no power source that will have up to. Oh wait, oh there is. Let me not talk like that. Sorry, I was thinking to myself. Sorry. Oh, now I have to zoom in and zoom in and zoom in. I've written a lot on this mirror board. Anyway, okay, so this power that we've gotten now is the um voltage power output essentially that the battery that we need is going to need to be able to supply for us. And then we have been told that it is advisable for you to use 80% of the battery life that is being supplied in realistic terms, or 70. So if we are going to calculate the efficiency, okay, so let's assume, sorry, so based on the criteria that we have now, honestly speaking, I do not think that there is any battery that can supply 200 amps, or there are realistically, and then 120 volts, but it may not just be able to supply it for a long period of time. May not just be able to supply for a long period of time. So what I usually do is I would now browse the type of battery that I want to use. Yeah, and since we are working with a battery that I honestly do not, I think the highest battery source that can be supplied is there are 6S. 6S is 3.7 times 6, and that is, or the highest I've seen is even 4S sef. Hmm. No, there is actually 6S. So there are batteries that can solve. Wait, okay. So we need a 120 volts battery. Hmm. Okay, so we've seen the battery criteria that we need, sure, and there are batteries like that exist. So based on the ratings that you have or that you've calculated, it may be possible for you to get power sources or batteries that have it. But to be honest with you, they're not really standard, and they don't exactly exist in Nigeria. Okay, sorry, we have them, but they are not readily available in Nigeria. That's what I'm trying to say. So, mm most times what I would just do is I will check, let's say, the plugs that I have, and check the highest battery rating that they have. And then once I now get that, I would now like reverse engineer. I would now reverse engineer it to see if or how long this battery, if I use it, how long is it going to last? How long it is going to last? Each wrong option. How long it is going to last, and then based on how long it is going to last, I will now use that to calculate the efficiency and the battery life of that battery, essentially. So we are all so basically this is just me trying to teach you guys of how to make the best with what you have. But I know that the store that usually has like heavy duty batteries is for 360. I feel like I'm just giving these people free adverts. Sha sha sha. That's by the way. I don't think microscale will have them. Mm, sorry, hold on. I don't think microscale is going to have this thing that we are looking for. So you just prefer to go to Hub 360 and check. Hmm. Now imagine if we were actually using like four brushless DC motors instead of, sorry, if we were using six instead of four. Oh, battery that will need and you have to realize that, yep, I was right. Microscale does not have. You have to realize that heavy duty projects require um heavy duty power, heavy duty batteries, basically. Heavy duty batteries. What else type batteries? So you guys can see the amount of, there is like a bit of trial and error in this thing. Okay, so actually, so this battery, the office that I work at, I think we actually bought this thing in October last year. And even still, it was not able to do what we needed it to do because the current rating was not enough. It's actually as much as 5,200 milliamps looks like a lot, it is actually not. So the what is the word? The load, it was not enough to support the load that the project needed. And then we needed to buy new batteries or reverse engineer it. And even to today, I've not done the necessary calculations to reverse engineer it. So I think this battery is actually the one with the highest rating that they have on Up 360. So I think we'll just work with that one and then try to use that to calculate the efficiency of the battery and how long under these circumstances this battery is going to last without until you now have to charge it. Okay, I think this is the highest. Is this the highest? It's the same. This is 11.1. I think it's the same thing, but why is it more expensive? Is it the producer? Why is it more expensive? That's weird. Anyway, let's keep going down. Let's keep going down. This one is 6 volts, 4 points. You're not helping. 4 points. Listen. Okay, I think that one that we passed is actually the one with the highest rating that is available. Yeah, I think that's the one with the highest rating. So let's work with this battery and let's see how long this battery is going to last with this um how long the battery is going to last in this project that we want it to do. Mm, mm, Sorry. Okay. So where was I? So let's come back. Let's share this. So the power rating that we shall found, or the kidney with the power rating that we shall found was 11 volts, 11.1 volts, and 5,200 milliamp hours. With this that we need. So this is the power output, this power input. The efficiency of this battery will be the power. um, okay, power out that is giving out over power in times 100. That's the efficiency of this battery. And in this case, the power output is going to be what? I think this is actually the input, so it's the other way around. Okay. So 24K 084.74. Sorry, if at any point I've lost you, please let me know so that I'll slow down. And I hope you guys can actually see my screen. I'll know what I'm doing. Oh, sorry, so that I'll know that we're together rather. Okay. So this over the power of this now that we have 11, 11, 11.1 times 5,000. Or we can just say 5.2. 57 point. eh, Okay, I think in this case it's going to be the higher number over the lower number. So I'm not going to do it this way. I'm going to wipe this part and then zoom in. And then write it like this to be the lower number over the higher number because I don't want to do nonsense. And I got, what did I get again? I got, why do I keep canceling this calculator? I wonder. What did I get before? Calculator. 11.1 times 5.2. 11.1 times 5.2. 57.72. And I cancel the calculator again. Princess, clap for yourself. 24,000 approximately times 100. Like there's actually something wrong with my calculation. But now, I think in the case of this thing that we can actually remove the power rating for the ESCs. Sorry, for the not the power rating for the ESCs, the power rating for the brushless motors, because I think we can actually remove it. Because the ESCs are what are going to be supplying power to the what's the name of this thing? To the brushless motors. I think I can actually wipe this out. And the ESCs in this case supplied 30 amps. So if they needed 30 amps to run, okay, so I'm going to wipe this part out. And because I'm wiping this part out, a lot of our values are going to change. Because if the ESCs are what are going to be driving the brushless motors, so as long as you can supply electricity to the ESCs, should be able to supply electricity to the brushless motors. So before we had 200.37. So I'm going to subtract 80 from it because I removed that of this thing. So we have 120.37 now. Okay, so 120.37. You guys understand the reason why I removed it, right? Because if the I think I've explained this already. You guys shall understand the reason why this thing. The reason why can you the reason why what's the word I'm looking for? The reason why I removed the ratings for the ESCs. I hope you shall understand that part. So moving to the calculator. So that's 120.2 times 120.37. And that's 14,468. 14,000. Oh, I'm going to have to erase so many things. Okay. I'm so sorry, my this thing is so messy. Let me try to zoom in and write it better. So power is current times voltage. That's 14,000. Please don't tell me that I cancelled it. I did. Sometimes I just wonder what goes on in my head. 120 points. 14,468. 468. 468.4474. Yeah. Yeah. So so what we are now working with is this, and it's now going to be this. So I'm going to wipe it. 14,468.474. Somebody help me calculate this. Help me calculate this so that I know that we're together in this class because I need feedback. So 57.72 over 14,468.474. Somebody please calculate it times 100 and let me know. Okay. So I got 0. Hmm. So um I got 0.4 approximately. 0.4. 0.4%. That is the efficiency of this battery. How long is this battery going to last under normal circumstances? That is How long is this battery going to last under normal circumstances? Okay, how long is this going to last? So the battery life in this case is battery life is um battery life is battery okay battery life is battery capacity in over device consumption. In this case, power in over power out. Because they usually say that you should only use 70 to 80% of, sorry, 70 to 90% of your battery capacity. Because if you aim to use the total 100%, you can actually damage your battery. So let's say since it's 70 to 80, sorry, 70 to 90, let's say we want to use 70% of this battery's capacity. 70% is 0.7. So this is how we're going to calculate it. And then taking it up, we now have 7 points. Let's keep in mind that this is in hours. So this is this is in hours. So we have 72 over what is this 14 what 14468 0.74 0.74 times 0.7. Now let's calculate it. 10 times 0.7, sorry, divided by 14468.74. This is in hours. 60, let's do times 60. Which, sorry, let me calculate it again. 4772 and 0.7 divided by 1468.74 times 60. Times 60 again. Okay, so what I got was, let's do this divided by 60, divided by 60. What I got was 0.0027 hours, which when you multiply by 60 will give you 0.167 minutes, which is 10 seconds. So this is how long this battery is going to last if you actually build it or use it. So yeah, this battery is very, very inefficient since it lasts for only 10 seconds. So we need a more heavy duty battery. Does that make sense? So a lot of times you have to do a lot of trial and yeah, exactly. Okay, thank you very much. So you have to do a lot of trial and error a lot of times and see which battery better fits what it is you are looking for. And in this case, this battery, which happens to be the most heavy duty battery, is not going to last for this project, unfortunately. That's if it hits like the maximum voltage and current that this each of these components require. So how did we get here? We got the maximum input voltage and input current of all the components, added all of them together, calculated that use it to calculate the power. When we got the power, we got a, let's say, the highest duty battery that we could have found at our disposal, and then we use that to calculate the efficiency, and we got 0.4. Then as we did that, we now use that this battery capacity, took 70% of it, and then now use that to calculate how long the battery was going to last, and we got 10 seconds. So that is it for the majority of the time. But in most cases, it's not going to be like this because you would barely ever reach the maximum. We're just saying in worst case scenario, this battery is going to last for just 10 seconds in the worst case scenario. So do you get it? Does that make sense? Does anybody have any questions before we call it a day and we go home? So in most cases, when you now have like all the criteria, it's better you find a battery that is reasonably close enough, because when we calculated the voltage, we got something along the lines of 220, and we can see that it's actually possible to get a battery that is 220 volts, but not in Nigeria. You have to order it. So yeah, I think that brings our class to an end, and I'll be stopping here, and this will be our final embedded systems class. From here on, um from here on we will be sorry from here on we will call this a close, bring a close to today's class, and then we will have our last PCB design class tomorrow, where we'll be wrapping up, and then I'll be making an announcement in that class. So please, let's all make sure yeah, so let's all make sure that we are there and on time for tomorrow's class. Yeah, let's all make sure that we're on time for tomorrow's class. So thank you very much, everybody. Yeah, thank you very much. And I'll be sure to send the link and drop any other thing. Please don't forget to do your assignments also. The assignments that Falabi gave and the assignments that Ebuka also gave. So please, let's just make sure that we do that. Let me stop the recording here. So good night, everybody. See you all tomorrow.